The universe is a stage of endless mystery, where the laws of physics twist into the inexplicable and the unknown dances just beyond our reach. Picture this: a black hole so massive it bends light into impossible shapes, or a star that pulses like a cosmic lighthouse, sending signals across the void. These aren't scenes from a science fiction novel. They're real, bewildering phenomena hiding in the depths of space, waiting to shatter everything we thought we knew about the cosmos. And tonight, we're about to uncover 30 of the most astonishing oddities, celestial secrets so strange, they'll make you question reality itself. Think of the night sky as a grand illusion, a tapestry of familiar constellations masking the chaos lurking beyond. Behind those twinkling lights are objects and events so bizarre, they defy logic. Planets that rain molten glass, galaxies spinning like ghostly whirlpools, and dark matter weaving an invisible web that holds the universe together. What if I told you there's a place where time slows to a crawl, or a nebula glowing with colors no human eye has ever seen? These aren't just curiosities, they're cosmic riddles begging to be solved, each one a piece of a puzzle far grander than we've ever imagined. This isn't just a journey through space, it's an expedition into the unimaginable. Whether you're a seasoned stargazer or someone who simply gazes up in wonder, these revelations will leave you spellbound. We'll traverse the edges of known science, venturing into realms where the rules break down and the impossible becomes routine. By the time we're done, you'll see the universe not as a static backdrop, but as a living, breathing enigma, full of wonders that challenge our very understanding of existence. So buckle up, the cosmos is about to reveal its strangest secrets, and trust me, you won't believe what's out there. Deep in the heart of the Perseus galaxy cluster, something impossible echoes through the void, a black hole singing. Not metaphorically, not poetically, literally. NASA Chandra X-ray Observatory captured something extraordinary: pressure waves rippling through the superheated gas around the black hole, vibrating at a frequency 57 octaves below middle C. When scientists converted those waves into sound, the result was a single, sustained note, a cosmic bass so deep it would shake the bones of the universe itself if we could hear it unaided. So how does a black hole, an object so dense that not even light escapes, produce sound? The secret lies in the surrounding gas. Supermassive black holes are messy eaters, and as they devour matter, they belch out enormous jets of energy. These eruptions create shockwaves that travel through the cluster's gas like ripples in a pond. Normally, space is silent, a vacuum where sound can't travel. But here, the gas is so thick, so searingly hot, it acts like a medium, carrying those vibrations across millions of light years. What makes this even stranger is how rare it is. Most black holes don't sing because their surroundings are too sparse, but Perseus's black hole sits in a dense bath of gas, turning its eruptions into an eerie symphony. Scientists amplified the sound waves up quadrillions of times just to make them audible to human ears, revealing a note so haunting, it's been compared to the wail of a lonely star. And here's the twist: that note has been resonating for over 2 billion years. Imagine a single tone, deeper than anything on Earth, humming relentlessly across the eons. It's not just a curiosity, it's a clue. By studying these vibrations, astronomers can map the structure of galaxy clusters, unraveling how they grow and evolve. So the next time you look up at the night sky, remember, the universe isn't silent. Somewhere out there, in the fathomless dark, a black hole is still singing, its voice a whisper from the abyss, telling stories we're only beginning to understand. Somewhere in the constellation Cancer, 40 light-years from Earth, a planet shimmers with impossible extravagance, 55 Cancri E, a world that might just be the ultimate cosmic status symbol. Imagine a planet twice the size of Earth, where mountains could be literal diamonds and rivers might flow with liquid carbon. This isn't science fiction, It's what happens when a planet forms under the most extreme conditions imaginable, rewriting the rules of what's possible in planetary science. Astronomers first noticed something strange about 55 Cancri E when they studied its host star, a sun-like orb unusually rich in carbon. The planet orbits so close 8 times nearer to its star than Mercury is to our Sun, that a single year lasts just 18 hours. Surface temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize rock. But here's the twist: under that blistering heat, the planet's carbon-rich composition may have crystallized into something extraordinary. High pressure and scorching temperatures can force carbon atoms into a diamond lattice structure, meaning vast portions of this world could literally be made of solid diamond. What makes this discovery so revolutionary isn't just its extravagance, it's the challenge it poses to how we think planets form. Conventional wisdom suggested that rocky planets like Earth coalesce from silicon and oxygen, with carbon as a minor ingredient. But 55 Cancri E flips that script, proving that under the right conditions, carbon can dominate, creating an entirely new class of planet. Some scientists even speculate that beneath its diamond crust, the pressure might be so intense that carbon transforms into exotic forms we've never seen. Perhaps even metallic carbon, a material that could conduct electricity in ways that defy our understanding. Then there's the atmosphere, or lack thereof. Radiation from its nearby star likely strips away any gases, leaving the diamond surface exposed to the vacuum of space. But recent observations hint at something even stranger: a thin, shimmering haze. Could it be vaporized diamond, a glittering mist rising from the surface before condensing back into solid form? The possibilities are as dazzling as the planet itself. 55 Cancri E forces us to rethink the diversity of worlds. If a planet made of diamond exists, what else is out there? Planets of solid metal, worlds of sapphire or graphite. This glittering oddity isn't just a cosmic curiosity, it's a key to unlocking the infinite variety of planetary systems waiting to be discovered. And somewhere in the silent darkness of space, it continues to spin, a diamond in the rough of the cosmos, reflecting starlight like a beacon of the universe's endless creativity. The Milky Way isn't drifting through space aimlessly, it's racing toward something unseen at over 1 million miles per hour, caught in the grip of a cosmic mystery so vast, it reshapes our understanding of the universe. This is the Great Attractor, a gravitational anomaly so powerful it's pulling entire galaxies, including our own, toward a point in space we can't even see. Hidden behind the dense stars and dust of the Milky Way's disk, in a region astronomers call the zone of avoidance, this enigmatic force challenges everything we thought we knew about the large-scale structure of the cosmos. At first, the Great Attractor seemed like a glitch in the data, an unexplained tug on galaxies that shouldn't exist. In the 1970s, astronomers mapping the motion of galaxies noticed something bizarre. Instead of scattering evenly as the universe expanded, thousands of galaxies were streaming toward the same patch of sky near the constellations Centaurus and Hydra. The force behind this movement was equivalent to tens of thousands of Milky Ways packed into a single region of space. But when scientists pointed their telescopes in that direction, they found nothing. Or at least nothing obvious. The Great Attractor's home, the zone of avoidance, is obscured by our own galaxy's gas, dust, and stars, making it one of the most frustrating blind spots in modern astronomy. So what is pulling us in? The leading theory points to an unimaginably massive concentration of matter, perhaps a supercluster of galaxies so dense, its gravity warps the motion of everything around it. In the 1990s, astronomers discovered the Norma cluster, a gathering of galaxies roughly 250 million light-years away, sitting near the heart of the Great Attractor's pull. But here's the catch: even the combined mass of Norma and its neighboring clusters isn't nearly enough to explain the sheer scale of the phenomenon. That means something even bigger must lurk in the shadows. Some researchers suspect the Great Attractor might be just the tip of the iceberg, a small part of an even larger structure, like the Laniakea supercluster, a cosmic filament spanning 500 million light-years, with the Great Attractor acting as its gravitational anchor. Others propose more radical ideas. Could it be a remnant of a primordial flaw in the fabric of space-time, a concentration of dark matter so dense it bends the universe around it? Or something else entirely, something we haven't even conceived of yet? What makes this mystery so thrilling is what it reveals about our place in the cosmos. The Great Attractor reminds us that even as we map the universe, vast stretches remain hidden in plain sight. Every breakthrough peels back another layer of the unknown, proving that the universe is stranger, more dynamic, and more interconnected than we ever imagined. And as our telescopes grow more advanced, as we learn to see through the zone of avoidance, we might finally uncover the truth behind the force that's pulling us relentlessly into the dark. In the constellation Monoceros, 700 light-years from Earth, there's a cosmic structure so precise it looks like it was drawn with a ruler, the Red Rectangle Nebula. Unlike the swirling chaos of most nebulae, this one defies expectations with its sharp geometric symmetry, a glowing red X framed by ladder-like rungs of dust and gas. The closer astronomers look, the more baffling it becomes, because nothing in the universe should naturally form right angles like this. At the heart of the nebula lies HD 44179, a dying binary star system in its final act. As the aging stars shed their outer layers, they eject material in opposing jets, sculpting the surrounding gas into this uncanny shape. But the real mystery isn't just the structure, it's the color. The red rectangle owes its vivid hue to a rare form of organic molecules called polycyclic aromatic hydrocarbons, or PAH. These carbon-rich compounds, forged in the star's death throes, fluoresce under ultraviolet light, painting the nebula in shades of crimson unseen anywhere else in the cosmos. What makes this nebula so valuable to science isn't just its beauty. It's a laboratory for understanding how complex molecules spread through space. The same pHs found here have been detected in meteorites and even the haze of Saturn's moon Titan, hinting that dying stars like this one might seed the universe with the building blocks of life. Some researchers theorize that the red rectangle's dust could hold clues to how carbon, a key ingredient for life, gets distributed across galaxies. And then there's the shape. How does a turbulent stellar wind create something so orderly? The answer might lie in the binary stars themselves. Their orbital dance could funnel ejected material into those precise jets, like water spiraling down a drain. But even that doesn't fully explain the ladder-like rungs, which appear too regular to be accidental. Could there be magnetic fields guiding the dust, or some unseen physics at play? The red rectangle is more than a cosmic oddity. It's a reminder that even in death, stars create. As HD 44179 fades, its final masterpiece glows on, a fleeting monument to the universe's ability to turn chaos into symmetry. And long after the central stars have dimmed, the molecules forged here might drift through space, finding their way into new solar systems, new planets, perhaps even new life. Most galaxies dine politely, drifting through the cosmos in quiet isolation. But not NGC 5128, better known as Centaurus A. This celestial predator is a galactic cannibal, shredding and swallowing smaller galaxies whole, and the evidence is written across its twisted face in streaks of cosmic debris. At first glance, it looks like a violent accident, a messy collision frozen in time. But this is no accident. It's a deliberate feast, one that's reshaping our understanding of how galaxies grow. Centaurus A sits 11 million light-years away, close enough for telescopes to reveal its gruesome anatomy. Most galaxies fall into neat categories: spiral, elliptical, or irregular. But Centaurus A defies them all. At its core lies a monstrous elliptical galaxy, but slicing across its center is a thick, jagged dust lane, a scar left behind from a recent meal. This dark band is all that remains of a spiral galaxy it ripped apart, its stars and gas now digested into the larger structure. The sheer violence of this process is staggering. When galaxies collide, they don't crash like solid objects, they merge like ghosts, their stars slipping past one another, drawn together by gravity, but the gas and dust between those stars. That's where the real carnage happens. As the smaller galaxy spirals inward, tidal forces stretch it into ribbons, compressing gas clouds until they ignite with new star formation. Meanwhile, the supermassive black hole at Centaurus A's heart gorges on the influx of material, spewing jets of radiation that stretch 14,000 light-years into space. What makes Centaurus A so special isn't just its appetite, it's the menu. By studying its dust lanes, astronomers have reconstructed its last few meals, revealing a diet rich in dwarf galaxies. These cosmic snacks are crucial to galactic evolution, acting like nutrient supplements that deliver fresh gas and young stars to aging galaxies. Without them, giants like Centaurus A, and eventually our own Milky Way would starve, running out of fuel for new stars. And that's where things get personal. The Milky Way is no stranger to galactic cannibalism. We've already absorbed dozens of smaller galaxies, leaving behind streams of stars like crumbs from a feast. But in about 4 billion years, we'll collide with Andromeda, our nearest spiral neighbor. The result, a chaotic merger that could turn our serene galactic home into something resembling Centaurus A, a messy hybrid, its orderly spiral arms shredded into swirling dust lanes. Yet there's a strange beauty in this destruction. Centaurus A teaches us that galaxies aren't static islands, they're living, evolving beings, growing through violent mergers that seed new generations of stars. Those dark dust lanes, they're not just scars, they're birthmarks, proof of a galaxy constantly reinventing itself. And somewhere in the distant future, the Milky Way's own fate may be written in similar streaks of cosmic dust, a testament to the universe's endless cycle of creation and destruction. In the vast quiet of space, some sounds defy explanation, none more baffling than fast radio bursts or FRB. These are not your typical cosmic signals. Imagine a pulse of radio energy so intense, it outshines entire galaxies in a fraction of a second, then vanishes without a trace. First discovered in 2007, these bursts last just milliseconds, yet pack as much energy as the sun emits in 80 years. The strangest part, they're unpredictable, flashing across the cosmos with no discernible pattern, leaving astronomers scrambling to decode their origins. At first, some dismissed them as glitches, cosmic static, or telescope malfunctions, but then they kept repeating. In 2016, astronomers traced one burst, FRB 121102, to a tiny galaxy 3 billion light-years away. This discovery confirmed FRBs weren't local quirks but phenomena from the distant universe. The plot thickened when some bursts began repeating sporadically, like a celestial Morse code, while others flared once and went silent forever. What could possibly produce such brief, monstrous explosions of energy? Theories range from the plausible to the extraordinary. Leading candidates include magnetar neutron stars with magnetic fields so strong they could strip the data from a credit card halfway across the Milky Way. When these hypermagnetic stars experience starquakes, their crusts crack, releasing bursts of energy that might explain some FRBs. Then there's the possibility of colliding neutron stars or black holes, cosmic crashes so violent they send shockwaves rippling through space-time. But the most tantalizing and controversial idea, alien technology. Some scientists, like Harvard's Avi Loeb, have speculated that FRBs could be signatures of advanced civilizations, perhaps massive energy beams used to propel light sails across galaxies. It's a long shot, but not impossible. After all, the universe has surprised us before. Take the infamous WOW signal, a 72-second radio burst detected in 1977. It matched the expected signature of an artificial transmission so perfectly that the astronomer who discovered it scribbled "Wow" in the margin of the data printout. Decades later, we still don't know what caused it. Here's what makes FRBs revolutionary. They're not just cosmic oddities, they're tools. As these bursts travel across the universe, they interact with the sparse matter between galaxies, slowing slightly in ways that reveal the universe's hidden structure. Astronomers now use them to map the cosmic web, the vast invisible filaments of gas that weave the cosmos together. Each burst is like a flare in the dark, illuminating the shadows between galaxies. Yet for all their brilliance, FRBs remain one of astronomy's greatest puzzles. Why do some repeat while others don't? How can something so fleeting unleash such staggering energy? And could there be a connection to other unsolved mysteries like dark matter or quantum anomalies? Every new detection peels back another layer, but the truth still dances just out of reach. One thing's certain, in a universe full of whispers, FRBs are the shouts, loud, urgent, and impossible to ignore. And somewhere out there, the next burst is waiting, ready to rewrite the rules once again. Saturn's North Pole hides a storm so precise, it looks like it was etched by the hand of some cosmic architect, a perfect hexagon wider than two Earths placed side by side. This six-sided behemoth has churned in the planet's upper atmosphere for at least 4 decades, possibly much longer, defying every expectation of how fluid dynamics should behave. Hurricanes on Earth spiral into familiar circular shapes, their chaos governed by wind and rotation. But Saturn's hexagon, it's a geometric enigma, its razor-sharp angles and near-perfect symmetry standing untouched by the planet's raging winds. When Voyager first glimpsed this anomaly in the 1980s, scientists initially doubted their own instruments. How could a gas giant, a world without solid surface features, generate such a rigid, polygonal storm? Follow-up observations by Cassini revealed the hexagon wasn't just a fleeting illusion. Towering walls of cloud stretched 60 miles high, rotating in sync with Saturn's deep interior like a colossal cosmic gear. The winds at its edges scream at over 200 miles per hour, yet the hexagon's shape remains eerily stable, unbent by the turbulence around it. The leading theory points to Saturn's unique atmospheric jet streams. On Earth, jet streams meander, shifting with temperature and terrain, but Saturn's rapid rotation once every 10.5 hours may force its upper winds into standing waves, much like how water in a spinning bucket forms stable ridges. Laboratory experiments using spinning fluids have recreated polygon shapes, suggesting the hexagon could be a resonant pattern where atmospheric waves lock into geometric harmony. Yet mysteries linger. Why 6 sides? Why not a pentagon or an octagon? Some models suggest the number relates to the speed difference between Saturn's inner and outer layers, with 6 being the sweet spot where opposing forces balance. Others propose more exotic explanations, like hexagonal convection cells rising from deep within the planet's metallic hydrogen core. Then there's the hexagon's eerie color shifts, changing from golden to blue as Saturn's seasons slowly turn, hinting at chemical processes we've yet to decode. What makes this storm truly humbling is its endurance. Earth's largest hurricanes dissipate in weeks. Jupiter's great red spot, while centuries old, constantly shifts in size and shape. But Saturn's hexagon, it's a celestial monument to order amid chaos, a reminder that even in the whirlwind, the universe finds ways to carve perfection. And as Cassini's final transmissions revealed, its 6-sided dance continues unabated, a silent, spinning sentinel guarding the secrets of Saturn's sky. Stars aren't supposed to cheat death. When a massive star exhausts its fuel, it dies in a catastrophic supernova explosion, a brilliant, one-time event that scatters its remains across the cosmos. But in 2014, astronomers spotted a star that refused to follow the rules. Designated IPTF-14 HLS, this bizarre object didn't just explode once. It erupted, faded, and then exploded again and again and again, like a cosmic phoenix trapped in an endless loop of destruction and rebirth. At first glance, IPTF-14 HLS looked like a typical supernova, a sudden flare in the sky bright enough to outshine its host galaxy. But then it did something unprecedented. Instead of dimming after a few months, it lingered, pulsing with violent outbursts over years. By 2017, it had brightened and dimmed at least 5 times, each explosion rivaling the energy of an entire star. The heat signatures alone defied explanation, swinging wildly between temperatures that suggested completely different types of stellar deaths. Normally, supernovae leave behind either a black hole or a neutron star. This one, it just kept coming back. The leading theory suggests IPTF-14 HLS was no ordinary star, but a pulsational pair instability supernova, a rare beast so massive, its core becomes unstable long before death. In this scenario, the star's own gamma radiation is so intense, it converts into matter and antimatter pairs, destabilizing the core and triggering repeated eruptions. Each explosion blows off layers of the star while leaving enough behind to fuel the next detonation, like a bomb with an unstoppable fuse, but even that explanation falls short. Models predict such stars should be hundreds of times the mass of our Sun, yet IPTF-14 HLS appeared too small. Its host galaxy, a dwarf system devoid of heavy elements, shouldn't have spawned such a monster in the first place. And then there's the kicker: archival photos revealed a possible explosion in the same spot in 1954. If confirmed, it means this star has been defying death for decades, if not centuries. What makes this zombie star so revolutionary isn't just its defiance of physics, it's the questions it forces us to ask. Are pulsational supernova more common than we thought? Could they be the missing link between ordinary supernova and the hyper-energetic explosions that light up the early universe? Or does IPTF-14 HLS represent something entirely new, a stellar Lazarus acting out a script we haven't even written yet? One thing's certain: the universe loves a rebel. And as IPTF-14 HLS continues its ghostly dance, flaring, fading, and flaring again, it reminds us that even in the cold equations of astrophysics, there's always room for the inexplicable. Somewhere out there, a star is rewriting its own death scene, and we're lucky enough to watch. The universe isn't a random scatter of galaxies, it's a masterpiece of structure, woven together by invisible threads into a tapestry so vast it defies comprehension. This is the cosmic web, the skeleton of existence itself, a network of dark matter and glowing gas that stretches across the observable universe like veins in a celestial body. Picture this: galaxies aren't isolated islands but beads strung along these filaments, clustered at the intersections where the web is thickest, while between them yawn unimaginable voids, regions so empty they could swallow our entire local group of galaxies without a trace. Dark matter is the unseen architect of this web, its gravity sculpting the universe over billions of years. Though invisible, its presence is undeniable. Imagine tossing pebbles onto a stretched sheet. The way they create dimples that attract smaller objects is how dark matter bends space-time, drawing ordinary matter into its invisible embrace. Without it, galaxies would never have formed, but here's the twist: the cosmic web isn't static. It's alive with motion, with galaxies sliding along filamentary highways like cars on a freeway, pulled toward dense knots called superclusters. The scale of this structure is staggering. Some filaments span hundreds of millions of light years, thin tendrils of gas and dark matter so faint they were only mapped in detail within the last decade. Astronomers use techniques like redshift surveys, measuring how light from distant galaxies stretches as the universe expands, to trace the web's outline. The Sloan Digital Sky Survey revealed a slice of this architecture, showing how galaxies align along threads like pearls on a string, with voids between them so vast they're often called cosmic deserts. What makes the cosmic web so eerie is how it mirrors natural patterns on Earth, neural networks in brains, the branching of trees, even the internet's infrastructure. This isn't coincidence, it's a universal law of organization. Gravity works the same way at all scales, pulling matter into filaments whether it's shaping a galaxy or a droplet of water. But the web's true power lies in its role as a cosmic conveyor belt. Galaxies at filament intersections collide, merge, and ignite with star formation, while those stranded in voids fade into isolation, their stars burning out in quiet darkness. And then there are the voids, the web's shadowy counterparts. These are not just empty space, they're actively empty, their lack of matter pushing galaxies away like a repulsive force. The Boötes void, one of the largest known, spans 330 million light-years and contains barely 60 galaxies. If the Milky Way were stranded there, our night sky would be nearly black, with no nearby stars to light the abyss. Yet even these voids play a role, their boundaries acting as pressure chambers where gas compresses and sparks new galactic life. The cosmic web is more than a map. It's a chronicle of the universe's past and a predictor of its future. By studying its filaments, we're decoding how galaxies grow, how dark matter shapes reality, and perhaps even uncovering the fate of everything. Because one day, far in the future, the web's threads will stretch too thin and the universe will fade into darkness. But for now, it glows a luminous net cast across the cosmos, holding the story of existence itself. Moons shouldn't outshine their planets, but in the distant Kepler system, astronomers may have found one that does. Orbiting the gas giant Kepler 1625b, nearly 8,000 light-years away, is an object so enormous it shouldn't exist, a potential moon the size of Neptune. If confirmed, this exomoon would rewrite every rule we have about how moons form, pushing the boundaries of what's possible in cosmic mechanics. The story begins with Kepler 1625b, a planet 10 times heavier than Jupiter, lazily drifting through its star's habitable zone. When astronomers noticed tiny, periodic dips in the star's light distinct from the planet's own transits, they realized something extraordinary. Those fluctuations matched what you'd expect if the planet had a moon trailing it. Not just any moon, though. The data suggested a companion roughly 1.5% the mass of its host planet, making it nearly as big as the gas giants in our own solar system. For context, that's like Earth having a moon the size of Mars. Here's why this is revolutionary. Moons in our solar system fall into two categories: small, rocky bodies like Earth's moon, or mid-sized icy orbs like Jupiter's Ganymede. None approach planetary scale. Conventional models say moons form either from leftover debris after planet formation or from captured asteroids, neither of which could produce a Neptune-sized behemoth. So how did this one get there? One theory suggests a cosmic catastrophe. Perhaps two young gas giants collided, and the wreckage coalesced into a planet-moon pair. Another posits that the moon was once a free-floating rogue planet, snared by Kepler 1625b's gravity in a celestial game of capture the flag. But not everyone's convinced. The detection hinges on vanishingly faint light curves so subtle. Some researchers argue it could be noise in the data or even a second planet masquerading as a moon. Follow-up Hubble observations added fuel to the fire, revealing tantalizing hints of a gravitational tug between the two bodies, but the signal remained frustratingly ambiguous. The debate now hinges on a delicate question. Is this the first exomoon we've found, or just a cosmic mirage? What's at stake goes beyond one odd couple in deep space. Confirming Kepler 1625b's moon would prove that moons can form through processes we've never witnessed, processes that might be commonplace in the chaos of early planetary systems. It would also open doors to even wilder possibilities. Could there be habitable exomoons, worlds with liquid water and atmospheres, orbiting gas giants in other Goldilocks zones? Suddenly, the search for life isn't limited to planets alone. For now, the mystery lingers. Future telescopes, like the James Webb Space Telescope, may finally settle the debate by analyzing the system's atmospheric signatures. But whether this moon is real or not, its ghostly presence has already done something remarkable. It's forced us to rethink the limits of lunar possibility. Somewhere in the darkness, a gas giant may be circling a gas giant, a cosmic paradox waiting to be solved. The universe is supposed to be crowded galaxies clustered together like stars in a city sky. But in the constellation Boötes, there's a place so empty it defies logic. The Boötes Void, a spherical chasm spanning 330 million light-years where almost nothing exists. This isn't just a quiet neighborhood, it's a cosmic ghost town, a void so vast it could hold thousands of Milky Ways with room to spare. And yet, surveys count fewer than 60 galaxies inside it, a number so small it's like finding a single grain of sand in an Olympic-sized swimming pool. How does a void this extreme even form? The leading theory points to the cosmic web's architecture, the idea that dark matter's gravitational pull creates dense filaments where galaxies thrive, leaving behind empty voids where matter is scarce. But the Boötes Void isn't just empty, it's anomalously empty. Most voids still contain a faint scattering of galaxies. This one, it's a near-perfect vacuum, raising unsettling questions. Could it be the result of multiple smaller voids merging, like soap bubbles combining into one giant cavity? Or is there something more sinister at work? Some have proposed wilder explanations. Could an advanced civilization, a type Roman III civilization harnessing the energy of entire galaxies, have somehow cleared this region of space? It's a fringe idea, but not impossible. If a society reached unimaginable technological heights, they might dismantle stars for energy, leaving behind an engineered emptiness. Or perhaps the void is a signature of colliding universes, a bruise left behind by a parallel cosmos brushing against our own. These are speculative, of course, but the void's sheer scale demands creative thinking. Then there's the observational puzzle. The Boötes Void lies along a line of sight crowded with foreground stars and dust from our own galaxy, making it hard to study. Could there be faint, hidden galaxies we're simply missing? New telescopes like the James Webb Space Telescope are peering deeper, searching for dwarfs or ultra-diffuse galaxies that might solve the mystery. But so far, the void refuses to fill in. What makes the Boötes Void so haunting isn't just its emptiness, it's what it reveals about our place in the universe. If such a colossal nothingness exists, what other anomalies lurk in the darkness? And if voids this vast can form naturally, does that mean the cosmos is far stranger, far more unpredictable than we ever imagined? The Boötes Void doesn't just challenge our maps of the universe, it dares us to question how much we truly understand about the fabric of reality itself. Most planets orbit stars like obedient children, tethered by gravity's unbreakable leash, but not SIMP J01365663 plus 0933473. This cosmic rebel drifts alone through the Milky Way's dark frontiers, untethered from any star, a rogue planet with no sunrise, no sunset, just endless night. And it's not alone. Astronomers estimate billions of these nomads wander our galaxy, unseen and untracked, their existence betrayed only by the faintest whispers of infrared heat or the occasional gravitational lensing event. How does a planet end up orphaned? The scenarios read like cosmic horror stories. Some are violently ejected from their birth systems, catapulted into the void by gravitational slingshots during the chaotic dance of young planets. Others may form in isolation, collapsing directly from gas clouds too small to ignite into stars. SIMP Discovery was itself a fluke. A team scanning the sky for brown dwarfs stumbled upon its faint infrared glow, revealing a world 12 times Jupiter's mass, yet floating freely near our solar neighborhood. Without a star's light, its surface temperature hovers around 800 degrees Fahrenheit, hot enough to melt lead, but frigid by planetary standards. What makes rogue planets fascinating isn't just their loneliness, it's the possibility they harbor life. Conventional wisdom says life needs starlight, but imagine a planet like SIMP with a thick, hydrogen-rich atmosphere trapping geothermal heat from its core. Beneath that smothering shroud, tidal forces from a captive moon or even radioactive decay could sustain subsurface oceans. On Earth, extremophiles thrive in volcanic vents and ice-covered lakes. Why not in the abyss of a rogue world? Some models suggest these planets might retain atmospheres for billions of years. They're pressure cookers of chemistry quietly brewing who knows what. Detecting them, though, is like searching for a black cat in a coal cellar. Without starlight to reflect, they're nearly invisible. Astronomers rely on two tricks: microlensing, where a rogue planet's gravity briefly bends the light of a background star like a magnifying glass, and direct infrared imaging, picking up their residual heat. Even then, most are found by accident. The upcoming Nancy Grace Roman Space Telescope could change that, scanning for microlensing events at unprecedented scale, potentially uncovering thousands of these ghosts. Yet mysteries linger. Are rogues more common than star-bound planets? Could some have formed around stars in the early universe, only to be stripped away when their hosts died in supernova? And if life does exist on one, how would it adapt to eternal darkness, where the only light comes from bioluminescence or the rare flash of a passing star? SIMP and its kin force us to rethink the very definition of a planet, not as something that orbits, but as something that exists untethered and untamed. They are the cosmic drifters, the silent majority of worlds, forever roaming the great between. In the constellation Cygnus, 1,500 light-years from Earth, a star behaves like nothing else in the known universe. KIC 8462852, better known as Tabby's star, or Boyajian star, doesn't just flicker. It plummets in brightness, dimming by up to 22% at irregular intervals, as if something colossal is passing in front of it. Not a planet, not a typical dust cloud, something stranger. When astronomer Tabitha Boyajian first documented these bizarre dips in 2015, the data defied all conventional explanations, sparking whispers of alien megastructures and cosmic anomalies we're only beginning to unravel. The mystery lies in the star's erratic light curve. Most stars dim predictably, perhaps a planet transiting every few months or a companion star eclipsing it on schedule. But Tabby's star, its dips are sudden, asymmetrical, and deep. Some last days, others weeks, with no discernible rhythm. The most dramatic event, observed by the Kepler Space Telescope, saw the star's light drop 22% over just a few days, equivalent to something 50 times wider than Earth blocking its light. And then, as abruptly as it began, the dimming stopped. Early theories pointed to natural causes. Maybe a colossal swarm of comets, thousands of them, was spiraling into the star, their icy debris creating a patchy veil of dust. Or perhaps an enormous ringed planet, far larger than Saturn, was casting uneven shadows, but calculations revealed flaws in both ideas. A comet swarm that massive should have left infrared traces, warm dust glowing around the star. None was found. A mega-planet's rings would have produced more regular dips. These were anything but regular. Then came the wild card, the Dyson sphere hypothesis. Physicist Freeman Dyson once theorized that advanced civilizations might build energy-harvesting megastructures around stars, vast solar panels or habitats that would partially block starlight. Tabby's star's irregular dips seemed eerily consistent with such a construct, especially if it were incomplete or rotating haphazardly. The idea captured public imagination, but scientists urged caution. Extraordinary claims require extraordinary evidence, and the cosmos is full of oddities we've yet to understand. Subsequent observations tilted the scales toward natural explanations. Detailed spectroscopy revealed the dimming was wavelength dependent, meaning shorter wavelengths of light were blocked more than longer ones. That's a telltale sign of fine dust particles, not solid megastructures. Further studies suggested a circumstellar dust cloud, possibly debris from a shattered moon or a catastrophic planetary collision, could explain the erratic dimming without invoking aliens. Yet the puzzle isn't fully solved. Why does the dust distribution shift so dramatically? What caused the star's century-long secular dimming, a gradual fade observed in historical records? And could there still be a kernel of truth in the Dyson sphere idea, if not as a complete structure, then as some form of alien engineering we can't yet conceive? Tabby's star is more than a curiosity, it's a lesson in cosmic humility. Every time we think we've catalogued the universe's quirks, something like this forces us to rethink. Whether the answer is dust, debris, or something beyond our current science, one thing's certain: this star refuses to be ignored. It keeps blinking its cryptic signals across the void, daring us to look closer, to question deeper, and to remember that the universe always has one more surprise up its sleeve. The universe is expanding, that much we know, but something strange is happening at the edges of our cosmic map, a phenomenon so unsettling it challenges the very foundations of modern cosmology. Meet the dark flow, a mysterious collective motion of galaxy clusters hurtling toward the same distant point in space at unfathomable speeds. These aren't random drifts, they're coordinated, like leaves caught in a hidden current, all pulled toward something beyond the horizon of the observable universe. It started with the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped its subtle temperature variations, they noticed something impossible: clusters of galaxies moving en masse toward a region near the constellations Centaurus and Hydra at speeds exceeding 2 million miles per hour. That's faster than the universe's expansion should allow, and gravity alone can't explain it. There's no known structure, no supercluster, no cosmic filament massive enough to tug them in that direction. So what's pulling them? One theory dances on the edge of science fiction: other universes. Beyond the limits of our observable cosmos, there might lie regions of space-time with entirely different physical laws, perhaps even other Big Bangs. If one of these alien universes grazed our own in the distant past, its gravitational wake could be yanking our galaxy clusters toward it like a magnet dragging iron filings. It's a radical idea, but not impossible. The multiverse hypothesis, long relegated to theoretical physics, might suddenly have observable consequences. Skeptics propose a simpler answer: flaws in our models. Maybe we've misjudged the distribution of dark matter, or perhaps the cosmic microwave background isn't as uniform as we thought. But the data refuses to cooperate. Even after accounting for errors, the dark flow persists, its signals strengthening with deeper observations, the most unsettling possibility. We're seeing the fingerprints of a pre-Big Bang reality, relics from an earlier epoch when the laws of physics were fundamentally different. What makes the dark flow so revolutionary isn't just its mystery, it's the questions it forces us to confront. Are we missing a fundamental piece of cosmology? Is the universe vaster and stranger than we ever dared imagine? Or have we stumbled upon the first tangible clue of a reality beyond our own? Every new observation tightens the knot, leaving us with a humbling truth. The cosmos still keeps its deepest secrets hidden just beyond the edge of our understanding. And somewhere out there, in the uncharted dark, an unknown force continues to pull, its purpose as enigmatic as the flow itself. Among the countless galaxies drifting through the cosmos, few stop astronomers in their tracks like Hoag's object. This celestial wonder, floating 600 million light-years away in the constellation Serpens, looks less like a galaxy and more like a cosmic bullseye, a perfect luminous ring of blue stars encircling a golden core, with a yawning gap of near-total darkness between them. No spiral arms, no messy dust lanes, just a pristine, symmetrical loop of starlight hanging in the void like a piece of divine jewelry. The mystery begins with its structure. Most ring galaxies, like the famous Cartwheel Galaxy, form through violent collisions, smaller galaxies punching through larger ones, sending shockwaves through their gas and triggering star formation in a ripple pattern. But Hoag's object shows no signs of a recent impact, no debris, no warped disk, just that eerie, empty void separating the core from the ring. If it wasn't born from a collision, how did this perfect circle come to be? One theory suggests it's a cosmic fossil, a relic from a rare phenomenon called a resonance ring. Billions of years ago, the galaxy's rotating disk might have developed density waves, areas where gravitational forces squeezed gas clouds until they ignited with new stars. Over time, these waves could have organized into a stable ring, while the core aged into a dense yellow glow of older stars. But even this explanation feels incomplete. Why hasn't the ring collapsed inward or dissipated? What keeps the core so sharply defined? Then there's the puzzle of the gap. That dark band between the ring and the core isn't just empty space, it's suspiciously clean, devoid of the gas and dust that should naturally accumulate over billions of years. Some astronomers propose an ancient, stealthy black hole at the galaxy's heart, its gravity subtly clearing the area like a cosmic broom. Others wonder if the gap is evidence of a long-lost companion galaxy, its gravity tugging material away before vanishing into the abyss. But the weirdest twist, Hoag's object isn't alone. Peering through the darkness behind it, telescopes reveal another, fainter ring galaxy, an almost identical bullseye floating even farther away. Are these two cosmic twins the result of the same bizarre process? Or is the universe playing a trick on us, dangling clues we're not yet equipped to decode? What makes Hoag's object so mesmerizing isn't just its beauty, it's the questions it forces us to confront. Are we seeing a fleeting moment in galactic evolution, a structure so delicate it'll vanish in another billion years? Or is this the hallmark of an entirely undiscovered class of galaxies hiding in plain sight? For now, it spins silently in the dark, a perfect enigma, daring us to unravel its secrets. Some stars burn bright and fast, vanishing in cosmic blinks. Others endure, like HD 140283, the Methuselah star, a relic so ancient its age threatens to rewrite history itself. Nestled in the constellation Libra, this unassuming yellow subgiant holds a staggering secret. According to multiple measurements, it might be older than the universe. Here's the paradox. The universe, as we understand it, began 13.8 billion years ago with the Big Bang. Yet when astronomers first calculated HD 140283's age using its composition and luminosity, their answer sent shockwaves through the scientific community. 14.5 billion years, a number that blatantly defies cosmic chronology. How can a star exist before the universe that birthed it? The key lies in the star's extreme metal poverty. Unlike younger stars enriched by generations of supernova, the Methuselah star is almost pure hydrogen and helium, elements forged in the primordial furnace of the early cosmos. Its lack of heavy metals suggests it formed from nearly pristine gas, making it a second-generation star, one of the very first to ignite after the Big Bang. But even that doesn't fully explain the discrepancy. Revisions to the star's distance helped narrow the gap. Initial estimates placed it farther away, which skewed luminosity calculations and inflated its apparent age. Updated parallax measurements from the Hubble Space Telescope adjusted its distance to just 190 light-years, tweaking the age estimate downward to around 14 billion years, still uncomfortably close to the universe's birthday. Then came the real game-changer, refined models of stellar evolution. Stars like HD 140283 burn slower than we once thought, especially with their ultra-low metal content. Adjusting for this, plus accounting for helium diffusion within its layers, brought its age down to roughly 13.7 billion years, a hair shy of the universe's age. Crisis averted, not quite. The margin of error still leaves room for the star to technically predate everything, forcing astronomers to confront an even deeper question: could our cosmic timeline be off? Some speculate the universe might be slightly older than we think, perhaps due to errors in measuring the cosmic microwave background or misjudging the Hubble constant. Others propose exotic physics like variable dark energy densities that altered the early universe's expansion rate. Then there's the wild card. What if the Methuselah star isn't a singular anomaly, but a harbinger of a population of impossibly ancient stars we've yet to discover? What makes this star so humbling isn't just its age, it's the reminder that our cosmic clocks are still being calibrated. Every measurement, every model is a best guess built on layers of assumptions. HD 140283 glows quietly in the night sky, a silent witness to epochs we're only beginning to fathom, and a challenge to everything we think we know about time itself. Imagine a wave so powerful it could carve through the galaxy, sterilizing entire planets in its path, a tsunami of gamma radiation, invisible and deadly, rippling across the cosmos at nearly the speed of light. This isn't science fiction. It's the spine-chilling hypothesis of galactic superwaves, a controversial theory suggesting our Milky Way might periodically unleash apocalyptic bursts of energy capable of reshaping life on Earth. And the scariest part, some researchers believe these waves could be the hidden culprits behind some of our planet's most devastating mass extinctions. The idea traces back to astronomer Paul Laviolette, who proposed that the center of our galaxy, home to a supermassive black hole named Sagittarius A, doesn't just sit quietly. Instead, it might occasionally erupt in cataclysmic outbursts, sending shockwaves of cosmic rays and gamma radiation radiating outward like ripples from a stone tossed into a pond. These superwaves wouldn't just be brief flashes. They could persist for thousands of years, bathing star systems in radiation strong enough to strip atmospheres, mutate DNA, and trigger climatic chaos. Evidence for this theory hides in plain sight. If you know where to look, ice cores drilled from Antarctica and Greenland reveal strange, sudden spikes in radioactive isotopes like beryllium-10 and chlorine-36, dating back to periods coinciding with known extinction events. These isotopes form when high-energy cosmic rays smash into Earth's atmosphere, suggesting something, perhaps a superwave, once flooded our solar system with intense radiation. Then there's the geological record, layers of soot and iridium, markers of global fires and asteroid impacts that align suspiciously with these cosmic radiation spikes. Coincidence or the fingerprints of a galactic-scale disaster? But not everyone's convinced. Mainstream astronomy remains skeptical, pointing out that Sagittarius A shows no signs of such violent activity in recent millennia. Detractors argue the ice core data could be explained by nearby supernova or even fluctuations in Earth's own magnetic field. Yet the theory persists, fueled by tantalizing clues. Take the Geminga pulsar, a dead star roughly 800 light-years away. 1,200 years ago, it unleashed a gamma-ray burst so powerful it left scars in our planet's tree rings, proof that even a single stellar corpse can pack a punch. Now scale that up to a galactic core's fury. What makes superwaves so unsettling isn't just their destructive potential, it's their inevitability. If Laviolette is right, these events aren't freak accidents, they're cyclical, tied to the Milky Way's natural rhythms. Our solar system orbits the galaxy's center every 225 million years or so, passing through regions where radiation might be more concentrated. Could this explain why extinctions seem to follow a rough timetable? And if another superwave is due, would we even see it coming? Here's the twist: we might already be in one. Some researchers speculate that the rising incidence of cosmic rays detected in recent decades could be the leading edge of a subtle superwave, a prelude to something far more severe. It's a fringe idea, but one that forces us to confront an uncomfortable truth. The universe isn't just vast and beautiful, it's also volatile, capable of wiping the slate clean without warning. Whether superwaves are real or not, their specter lingers, a reminder that Earth's fate is tied to forces far beyond our atmosphere. And somewhere out there, in the heart of the galaxy, something may be stirring quietly, inexorably building toward the next great wave. Gravity doesn't just bend light, it plays tricks with it. Deep in the constellation Pegasus, 600 million light-years away, a cosmic illusion defies common sense. A single quasar, blazing at the edge of the observable universe, appears not once, but 4 times in perfect symmetry around a foreground galaxy. This is the Einstein Cross, one of nature's most elegant demonstrations of relativity, and a ghostly fingerprint of the unseen dark matter shaping our cosmos. At first glance, the 4 blue-white smudges look like unrelated stars, but their secret lies in the galaxy at their center. That unassuming spiral isn't just blocking our view, it's warping spacetime itself. According to Einstein's theory, massive objects bend light like a lens, magnifying and distorting anything behind them. In this case, the galaxy's gravity splits the quasar's light into multiple paths, each taking a slightly different journey around the galactic core before converging at our telescopes. The result, a celestial mirage so precise it looks engineered. What makes this illusion invaluable isn't just its beauty, its utility. Each image carries a unique timestamp. Since the light paths vary in length, fluctuations in the quasar's brightness appear in each image at different times, lagging by weeks or months. Astronomers use these delays like cosmic stopwatches, calculating the galaxy's mass and even measuring the universe's expansion rate with unprecedented precision. But here's the twist: the galaxy's visible stars and gas account for just a fraction of the lensing effect. The rest, an invisible halo of dark matter, its gravity betraying its presence like footsteps in snow. The Einstein Cross isn't alone. Only a handful of such perfect alignments are known, each a fluke of perspective so rare it's like threading a needle across the universe. Yet their implications are universal. By studying these crosses, we've mapped dark matter's distribution in ways impossible with traditional telescopes, proving it isn't smoothly spread but clumped in filaments and halos. Some models even suggest these lenses could magnify the earliest galaxies, acting as natural telescopes to reveal the universe's infancy, but the real magic lies in the math. Einstein predicted this effect in 1936, calling it a luminous ring too faint to ever observe. He underestimated technology and the universe's flair for drama. Today, the Einstein Cross stands as a monument to human curiosity, a reminder that even the strangest cosmic quirks can become our sharpest tools, and somewhere out there, another quasar waits, its light bent into yet undiscovered patterns, holding secrets we've only begun to trace. Death shouldn't breed life, but deep in the constellation Virgo, a cosmic graveyard defies that logic. Meet PSRB 1257 + 12, a pulsar so lethal it shouldn't have planets at all. This spinning corpse of a star, no larger than a city, packs the mass of our Sun into a seething ball of neutrons, blasting its surroundings with enough radiation to strip atoms bare. Yet somehow, against all odds, 3 worlds orbit this stellar zombie, survivors of a cataclysm so violent, it rewrote the rules of what a planetary system can be. The story begins with death. PSRB 1257 + 12 wasn't always a pulsar. Millions of years ago, it was a massive star that lived fast and died young, exploding in a supernova so powerful it should have vaporized any nearby planets. But when astronomer Alexander Wolskson pointed the Arecibo telescope at it in the 1990s, he detected rhythmic pulses in the star's radio emissions, tiny anomalies suggesting something was tugging on it. Not debris, not asteroids, planets. The discovery shattered expectations, proving worlds could form or persist in conditions once thought uninhabitable. What makes these pulsar planets so extraordinary isn't just their existence, it's their origins. One theory suggests they're the scorched remnants of the original system, planets that somehow clung to orbit as their star tore itself apart. Another proposes they're second-generation worlds, born from the ashes of the supernova itself. As the dying star ejected its outer layers, debris might have collapsed into a new disk, coalescing into planets like phoenixes rising from radioactive dust. The smallest of these worlds, dubbed Draugr, is twice the mass of Earth's moon, proof that even the tiniest survivors can endure the universe's worst tantrums. Then there's the radiation. Pulsars are cosmic lighthouses, emitting beams of X-rays and gamma rays so intense they'd cook a human in nanoseconds. Any atmosphere would be stripped away, leaving the planets naked to the onslaught. But life as we know it is stubborn. Could extremophiles exist deep underground, shielded by miles of rock, feeding on chemosynthesis like Earth's deep-sea vent creatures? Or stranger still, might life here rely on entirely unknown biochemistries, thriving in the pulsar's magnetic fields or drawing energy from the constant particle bombardment? The real twist: PSRB 1257 plus 12's planets aren't alone. Since their discovery, other pulsars have revealed similar planetary entourages, suggesting these undead systems might be more common than we thought. Each one challenges our definitions of habitability, forcing us to ask, if life can emerge in the aftermath of a star's self-destruction, where can't it take root? These irradiated worlds, spinning silently in their tomb of radiation, are more than cosmic oddities. They're testaments to the universe's relentless creativity, proving that even in the darkest corners, the seeds of persistence find a way. The cosmic microwave background should be smooth, a near-perfect snapshot of the infant universe's glow. But there's a glaring imperfection in this celestial portrait: the cold spot, a vast region in the constellation Eridanus where temperatures plunge mysteriously lower than their surroundings. This isn't just a minor fluctuation. Spanning nearly 2 billion light-years, the cold spot's chill is so extreme, it defies standard cosmic models. Some call it a bruise left by a collision with another universe. Others insist it's merely a trick of the light, but if it's real, it might be the first tangible evidence that our cosmos isn't alone. The cold spot's discovery sent shockwaves through cosmology. When the Planck satellite mapped the microwave background in unprecedented detail, this anomaly stood out like a frozen thumbprint. Statistical analyses suggest there's only a 2% chance such a feature could arise randomly from cosmic variance, raising the unsettling possibility that something truly extraordinary sculpted it. Enter the multiverse hypothesis. If multiple bubble universes exist beyond our own, constantly budding off from an ever-inflating cosmic foam, their edges might occasionally brush against one another. Such a collision could have left an imprint on our universe's early plasma, like a fingerprint pressed into soft clay. The cold spot, then, might be our first glimpse of an alien cosmos, a shadow cast by a reality with entirely different physical laws. Skeptics, though, aren't ready to rewrite textbooks. One camp argues the cold spot isn't a primordial relic at all, but the artifact of an enormous supervoid, a sprawling cosmic desert where galaxies are eerily scarce. As light traverses such a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolfe effect. The problem: surveys can't find a void large or empty enough to explain the cold spot's intensity. Another faction blames instrumental noise or overlooked systematic errors in the data. After all, the universe is under no obligation to conform to our theories, but neither is it obliged to serve up anomalies easy to interpret. What makes this debate so electrifying is the stakes. If the cold spot is proof of a multiverse, it would rank among the most profound discoveries in human history, shattering our cosmic solitude. Yet if it's merely a statistical fluke or measurement quirk, it's a reminder of how little we truly grasp about the universe's structure. The truth might lie somewhere between or beyond these options. Future telescopes, like the European Space Agency's Euclid mission, could settle the argument by mapping the distribution of galaxies and dark matter around the cold spot with unprecedented precision. Until then, it remains a tantalizing riddle, a cosmic Rorschach test where some see the fingerprints of alternate realities, and others see only the limits of our current understanding. Whether a window into the multiverse or a mirage in the data, the cold spot forces us to confront the humbling truth. The universe still holds mysteries no model can yet explain. Galaxies aren't supposed to collide with elegance. Cosmic crashes are meant to be messy, chaotic affairs. But in the constellation Canis Venatici, 23 million light-years away, NGC 5195 and its larger companion, the Whirlpool Galaxy, perform a gravitational ballet so precise it's rewritten the rules of galactic interaction. What makes this duo extraordinary isn't just their shared dance, it's the way their partnership has sparked a celestial fireworks show, birthing stars and warping structures in ways that defy expectation. The Whirlpool Galaxy, with its sweeping spiral arms, might seem like the star of the show, yet it's the smaller, seemingly unassuming NGC 5195 that holds the real intrigue. Classified as a dwarf galaxy, this cosmic underdog packs a gravitational punch far beyond its size. Over millions of years, it swung past the Whirlpool not once, but multiple times, each pass rippling through the larger galaxy's arms like a stone skipped across water. The result, a cascade of star formation so intense, Hubble's images reveal clusters of newborn stars glowing like diamonds strewn across velvet. But here's the twist, NGC 5195 isn't just a passive partner. As it tugs on the Whirlpool tugs back. The dwarf's own structure has been stretched and twisted, its once neat shape now a tattered streamer of dust and stars trailing behind it. This mutual distortion is a live-action lesson in tidal forces, gravity's way of pulling and kneading galaxies like cosmic dough, the most striking evidence. A vast filament of hydrogen gas, ripped from NGC 5195's belly during a close encounter, now arcs between the two like a celestial bridge. What makes this pairing so scientifically invaluable is the timeline. Unlike most interacting galaxies caught in a single snapshot of their collision, this duo offers a rare flipbook of galactic evolution. By mapping the Whirlpool's spiral arms, some tightly wound, others frayed, and chaotic astronomers can trace the sequence of their encounters, almost like reading tree rings. The youngest, brightest star clusters trace the most recent passages, while older, dimmer populations reveal the ghosts of interactions long past, yet mysteries linger. Why hasn't NGC 5195 been fully absorbed? Most dwarf companions succumb to their larger neighbors, vanishing into the galactic halo. This one persists, a testament to some unseen stability. Some simulations suggest it's on a highly elliptical orbit, dipping close before soaring away, delaying its inevitable assimilation. Others propose the Whirlpool's own rotation acts as a shield, slingshotting the dwarf outward with each pass. The deeper lesson here transcends astronomy. This cosmic duet reminds us that destruction and creation are two sides of the same coin. Every gravitational tug that warps a galaxy's shape also compresses gas, igniting new stars. Every collision that seems catastrophic plants the seeds for future beauty. And somewhere out there in the silent dark, NGC 5195 continues its slow, inevitable dance, a tiny partner in an endless waltz, proving that even in the vastness of space, no galaxy is ever truly alone. Globular clusters should be cosmic retirement homes, ancient gatherings of stars born together billions of years ago, all fading into old age at the same steady pace. But look closer and you'll spot rebels in the crowd, stars blazing hotter, brighter, and bluer than their peers, like teenagers crashing a senior's dance. These are blue stragglers, the ultimate celestial late bloomers, and their very existence defies everything we thought we knew about stellar evolution. The mystery begins with their color. In the stellar world, blue means youth, massive, energetic stars burning through their fuel at breakneck speed. Yet globular clusters formed in the universe's infancy, so every star here should have aged into a cool red giant or dim white dwarf by now. Blue stragglers break the rules, shining with the vigor of stars half their age. How? The answer lies in cosmic theft and stellar resurrection. One path to rejuvenation is sheer robbery. In the crowded core of a globular cluster, stars jostle like commuters in a packed subway. Close encounters can destabilize binary systems, allowing one star to siphon hydrogen fuel from its companion. This stolen gas reignites nuclear fusion in the thief's core, effectively hitting the reset button on its lifespan. Hubble observations have caught blue stragglers red-handed, some with unnaturally high levels of carbon and oxygen, telltale signs of a victim's outer layers splashed across their surface. Then there's the more violent option, full stellar mergers. When two stars collide, a rare but inevitable event in these dense clusters, their combined mass creates a single, hotter, more luminous star. Simulations show these mergers can produce stars up to twice the mass of their neighbors, explaining why some blue stragglers outshine everything around them. The evidence is written in their spin. Many of these stars rotate unnaturally fast, a cosmic hangover from the angular momentum of their catastrophic birth. But the real enigma isn't how they form, it's what they reveal about stellar survival. Blue stragglers force us to rethink the boundaries of a star's lifespan. If a star can cheat death by absorbing its neighbors, does age even mean anything in cosmic terms? And could this process explain other outliers, like the bizarre young stars spotted near the Milky Way's supermassive black hole? These celestial imposters are more than curiosities, they're time capsules. By studying their composition, we're decoding the secret histories of globular clusters, uncovering ancient collisions and thefts frozen in starlight. They prove that even in the quietest corners of the universe, stars refuse to fade quietly sometimes. They'll steal, crash, or reinvent themselves just to keep shining. Rising like colossal hourglasses from the Milky Way's core, the Fermi bubbles are one of the most baffling structures in our galactic backyard, twin towers of gamma-ray light stretching 25,000 light-years each, dwarfing every other feature in our galaxy. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these bubbles glow with the energy of 100,000 supernova, their edges razor-sharp against the darkness. But what carved these perfect, symmetrical voids into the fabric of our galaxy? The answer might lie in the most violent event the Milky Way has witnessed in millions of years. At the heart of the mystery is Sagittarius A, the supermassive black hole lurking at our galaxy's center. Normally, it's a quiet beast, no bigger than Mercury's orbit, nibbling on stray gas clouds. But the Fermi bubbles suggest a different past. One leading theory paints a picture of ancient chaos. Roughly 2.5 million years ago, Sagittarius A might have woken from its slumber, feasting on a star or gas cloud so massive, it unleashed twin jets of energy perpendicular to the galactic plane. These jets, rippling outward at near light speed, could have inflated the bubbles like cosmic bellows, leaving behind the gamma-ray afterglow we see today. Not everyone's convinced. Some astronomers argue the bubbles are too symmetrical, too perfect to stem from a chaotic black hole snack. They point to another culprit, a frenzy of star formation in the galactic center. When hundreds of massive stars ignite in quick succession, their combined stellar winds and supernova can blow enormous cavities into surrounding gas. The bubbles then might be the cumulative breath of a stellar nursery gone wild, a testament to the Milky Way's fiery youth. Then there's the dark horse candidate, dark matter. If hypothetical particles like WIMP, weakly interacting massive particles, collide and annihilate near the galactic center, they could produce gamma rays as a byproduct. The bubble's smooth, diffuse glow matches some models of such interactions, offering a tantalizing if speculative clue to dark matter's true nature. What makes the Fermi bubbles so electrifying isn't just their scale, it's their timing. 2.5 million years ago, Earth's hominid ancestors were just beginning to walk upright. If Sagittarius A did erupt back then, the energy would have bathed our planet in radiation. Curiously, geological records from that era show a spike in radioactive isotopes iron-60 in deep-sea sediments, hinting at nearby supernova activity. Could the bubbles be part of that same cosmic storm? For now, the debate rages on. New data from gamma-ray telescopes and simulations of galactic dynamics inch us closer to an answer, but the bubbles remain a Rorschach test for astrophysicists, a blank canvas where theories collide. One thing's certain, their very existence proves our galaxy isn't the serene spiral we once imagined. Beneath its tranquil facade, the Milky Way harbors a volatile heart, capable of eruptions that shape its destiny and perhaps even ours. Most galaxies glitter with stars, their spiral arms or elliptical halos ablaze with billions of suns. But Dragonfly 44 is different. Floating 330 million light-years away in the Coma cluster, this shadowy enigma emits less than 1% of the light expected from its size, a cosmic phantom where darkness doesn't just dominate, it defines. Meet the ultimate dark galaxy, a place where the ordinary rules of creation have been rewritten, and the very nature of matter itself is called into question. At first glance, Dragonfly 44 seems unremarkable, a smudge of dim stars no bigger than the Milky Way. But when astronomers measured its rotation speed, the numbers made no sense. Stars on its outskirts whip around the core far too quickly for the galaxy's visible mass to hold them in orbit. The only explanation, an invisible scaffold of dark matter, so dense it outweighs the galaxy's stars by a staggering 10,000 to 1. That makes Dragonfly 44 99.99% dark matter, a ratio so extreme it's less a galaxy and more a ghostly net of unseen particles, with a few fragile stars caught in its weave. This discovery shatters expectations. According to standard models, galaxies form when dark matter's gravity pulls in gas to birth stars. But Dragonfly 44 appears to have missed the memo somehow, gathering a titanic halo of dark matter while barely managing to spark a handful of stars. It's like finding an empty factory the size of a city, its machinery intact but its assembly lines eerily still. Scientists call these ultra-diffuse galaxies, cosmic anomalies that force us to ask, was Dragonfly 44 doomed from birth, or is it a relic of some forgotten path of galactic evolution? Theories collide over its origins. One camp argues it's a failed galaxy, a place where normal star formation was strangled in its crib. Perhaps the Coma cluster's brutal environment stripped away its gas early on, leaving the dark matter untouched while snuffing out stellar potential. Others propose a more violent history. Maybe it's the mangled remains of several smaller galaxies torn apart by tidal forces, their stars scattered while their dark matter merged into this monolithic halo. Then there's the wild card. Could Dragonfly 44 be a rare window into dark matter's behavior, revealing how it clumps independently of regular matter in ways we've never observed? What makes Dragonfly 44 so revolutionary isn't just what it is, but what it implies. If this shadowy giant isn't alone, if the cosmos teems with similar dark galaxies, our census of the universe is woefully incomplete. Current telescopes might be missing an entire population of these phantoms, their stars too faint to spot. Worse, their existence could upend our understanding of dark matter itself. Most simulations assume dark matter is cold, slow-moving, and prone to clustering. But Dragonfly 44's diffuse stars suggest its dark matter might be warmer, or even interact with itself in ways that prevent dense star formation. The hunt for answers is on. New telescopes like the Vera Rubin Observatory are scanning the skies for more dark galaxies, while physicists refine their models to account for these outliers. Every discovery peels back another layer of the mystery, proving that the universe's greatest secrets aren't always hidden in the light. Sometimes they lurk in the darkest corners, waiting for us to ask the right questions. And somewhere out there, Dragonfly 44 drifts a silent sentinel at the edge of understanding, its true nature still shrouded in the very darkness that birthed it. Zeta Ophiuchi isn't just a star, it's a cosmic fugitive racing through space at almost 60,000 miles per hour with a shockwave glowing like a bow before a ship. This blue giant, 20 times the mass of our Sun, shouldn't be where it is. It belongs in a binary system tethered to a companion, but astronomers found it alone, plowing through interstellar gas so violently. The collision creates a visible shock front that glows in infrared light, a cosmic wake stretching 12 light-years across the void. The story behind this stellar runaway reads like a celestial crime scene. Millions of years ago, Zeta Ophiuchi orbited a massive partner, a star destined to die young. When that companion exhausted its fuel, it didn't fade quietly. It detonated as a supernova, unleashing energy so extreme, it blasted Zeta Ophiuchi loose like a slingshot. The recoil sent the surviving star hurtling into space, stripped of its sibling but carrying the scars of the explosion. Spectroscopy reveals traces of heavy elements in its atmosphere, debris from the supernova's fireball, a ghostly fingerprint of the cataclysm that exiled it. What makes Zeta Ophiuchi so mesmerizing isn't just its speed, it's the visible chaos it leaves behind. As the star rams into surrounding gas and dust, its radiation and stellar wind compress the material into a glowing arc, heating it until it shines like a neon sign in the cosmos. This phenomenon, called a bow shock, is rare enough among stars, but Zeta's is one of the most spectacular ever observed, a textbook example of how violence shapes the universe. Yet this renegade isn't alone. The Milky Way harbors dozens of hypervelocity stars, each with its own tale of escape. Some, like Zeta, are survivors of supernova. Others were flung from the galaxy's core by the gravitational slingshot of our supermassive black hole, Sagittarius A. One such outcast, designated S5HVS1, rockets through space at over 3 million miles per hour, fast enough to leave the Milky Way entirely, destined to drift forever in the intergalactic void. The implications are staggering. These stellar fugitives act as cosmic probes, their trajectories tracing the gravitational forces that shaped them. By studying their paths, astronomers can map the Milky Way's hidden mass distribution, including dark matter's elusive influence. And if stars can achieve such velocities, what else might be hurled into the abyss? Planets, asteroids, theoretically. Even a rogue planet torn from its star by similar forces could carry frozen life through the darkness, a nomad in the endless night. Zeta Ophiuchi's fate is sealed. With no companion to stabilize it, the star will burn fiercely and die young, its material scattered by stellar winds long before it slows. But for now, it streaks through the cosmos, a blazing testament to the universe's untamed power, where even the mightiest stars can become exiles in their own galaxy. Andromeda isn't just our galactic neighbor, it's a cosmic predator, a silent devourer of worlds. This sprawling spiral, 2.5 million light-years away, hides a gruesome secret in its halo, the mangled remains of galaxies it's torn apart and consumed over billions of years. Peering into its outer reaches, astronomers have found ghostly trails of stars' orphaned suns strewn like breadcrumbs, marking paths of ancient collisions. These stellar streams, some spanning hundreds of thousands of light-years, are the smoking gun of Andromeda's insatiable appetite, proof that even galaxies grow by destruction. The most striking relic is the giant stellar stream, a river of stars arching around Andromeda's disk like a noose. This isn't random debris, it's the shredded corpse of a dwarf galaxy, perhaps as massive as the Large Magellanic Cloud that ventured too close. Simulations suggest the victim orbited Andromeda for billions of years, each pass stripping away more stars until gravity finally ripped it apart entirely. The stars didn't scatter randomly, they followed the precise contours of their progenitor's orbit, creating a luminous scar that persists long after the galaxy itself ceased to exist. But the giant stream isn't alone. Fainter tendrils crisscross Andromeda's halo, evidence of at least a dozen smaller meals. Some, like the Eni Shelf and the Southern Stream, are so dense with metal-rich stars they hint at victims far more chemically evolved than typical dwarfs, possibly former spirals like our own Milky Way, reduced to skeletal remains. Others, like the vast, diffuse Triangulum Stream, suggest Andromeda isn't done yet, as globular clusters and star clusters still drift into its gravitational maw today. This galactic cannibalism isn't just about destruction, it's about rebirth. Every devoured galaxy injects fresh gas and young stars into Andromeda, fueling new generations of star formation. The victim's dark matter halos merge with Andromeda's own, swelling its mass and tightening its gravitational grip. Even now, the dwarf galaxy M32, a compact, enigmatic satellite, shows signs of being the stripped core of a once larger galaxy, its outer layers digested long ago. And here's where it gets personal. In roughly 4 billion years, Andromeda will set its sights on its biggest prize yet, the Milky Way. Hubble's observations confirm our two galaxies are hurtling toward each other at 250,000 miles per hour, locked in a collision course that will reshape both beyond recognition. The first pass won't be a direct hit, more of a gravitational sideswipe, but the tidal forces will be catastrophic. Spiral arms will shred, flinging stars into chaotic new orbits. Gas clouds will compress, igniting a firestorm of new star birth. And as the galaxies swing apart, then spiral back together over billions of years, they'll finally merge into a single, monstrous elliptical galaxy astronomers dub Milkdromeda. Our solar system, it'll likely survive, flung farther from the galactic core but otherwise unharmed. The night sky, though, will transform beyond recognition. Andromeda's disk will loom larger than the Moon, its dust lanes and star clusters visible to the naked eye. New constellations will form from the mingling of both galaxy stars, a celestial melting pot where suns born in different corners of the universe share the same sky. Yet even this apocalyptic merger is just another link in the chain. Milkdromeda will continue cannibalizing smaller galaxies, growing ever more massive until trillions of years from now, it too may fall prey to an even larger predator in the Virgo cluster. The universe has a way of balancing creation and destruction, of building giants only to tear them down. Andromeda's scars are a reminder. In the grand cosmic dance, no galaxy is ever truly safe. The Milky Way's fate is written in those streams of stolen stars, a future as inevitable as it is violent. So the next time you gaze at Andromeda's faint smudge in the night sky, remember, you're not just looking at a distant island of stars. You're staring into the eyes of the galaxy that will one day consume our own. Imagine a wind so fierce it doesn't just bend trees, it rewrites the fate of entire galaxies. That's the terrifying reality of quasar tsunamis, cosmic tempests unleashed by supermassive black holes, capable of sterilizing galaxies with winds screaming at millions of miles per hour. At the heart of this cataclysm lies Markarian 817, a seemingly ordinary galaxy 430 million light-years away until astronomers peered closer and discovered it was harboring one of the most violent forces in the universe. When a supermassive black hole feasts on surrounding matter, it doesn't just swallow quietly, it belches. The energy released transforms the black hole's vicinity into a quasar, a beacon of light so intense it can outshine its host galaxy. But the real destruction comes from the winds. As gas spirals toward the black hole, friction heats it to unimaginable temperatures, generating pressures that blast material outward in a torrential gale. These aren't ordinary stellar winds. In Markarian 817, observations from NASA Chandra X-ray Observatory revealed winds clocking speeds of 200 million miles per hour, carrying enough energy to blow away entire star-forming clouds like cosmic confetti. What makes these winds so apocalyptic isn't just their speed, it's their reach. Unlike the localized fury of a supernova, quasar tsunamis sweep across thousands of light years, scouring galaxies of the raw materials needed to birth new stars. In Markarian 817, the winds extend over 3 times the width of the Milky Way, stripping away gas so efficiently that star formation grinds to a halt. Astronomers call this quenching, a chilling term for when galaxies transition from vibrant stellar nurseries to silent graveyards, their futures snuffed out by the very black holes that once anchored them. The mechanics behind these winds border on the surreal. As the black hole's radiation rams into surrounding gas, it ionizes atoms, tearing electrons from their nuclei and creating a superheated plasma. Magnetic fields, twisted by the black hole's spin, funnel this plasma into collimated jets and broader outflows, like a fire hose spraying in all directions. The effect is a feedback loop. The more the black hole eats, the stronger the winds grow, until they reach a tipping point where they effectively starve their own food supply. It's a self-destructive frenzy, like a wildfire that burns so hot it consumes its own oxygen. Yet there's a bizarre elegance to this destruction. Without quasar tsunamis, galaxies might grow unchecked, their star formation running wild until they exhaust all available gas in a few frenzied billion years. These winds act as cosmic regulators, balancing the chaotic birth of stars with the black hole's lethal embrace. Some theories suggest they're even responsible for the size limits of galaxies, preventing behemoths from forming by cutting off their gas supply before they grow too large. Markarian 817 isn't unique. Quasar tsunamis have been spotted in galaxies across the universe, their signatures etched in X-ray and ultraviolet light. But what makes this case so compelling is the detail. By studying its winds, astronomers have glimpsed the invisible forces that shape galactic evolution, revealing a universe where black holes aren't just passive monsters lurking in the dark, they're architects sculpting the cosmos with their fury. The implications stretch beyond a single galaxy. If these winds are as common as observations suggest, they could explain why the universe's peak star-forming era, 10 billion years ago, came to such an abrupt end. As quasars flared to life in countless galaxies, their tsunamis might have collectively silenced star birth, ushering in the quieter, more sedate universe we see today. So the next time you gaze at a distant quasar, remember, its brilliance isn't just a spectacle, it's a warning, a reminder that even in the vastness of space, violence writes the rules and black holes wield the pen. The moon's surface shouldn't have weather. No atmosphere means no storms, no wind, nothing but endless stillness. But there's an invisible tempest raging across its barren plains, the solar wind, a relentless stream of charged particles blasting from the sun at nearly 1 million miles per hour. Without Earth's protective magnetic field, the lunar surface should be utterly defenseless, bombarded day and night by this radioactive hail. Yet hidden in the moon's dusty crust lie bizarre anomalies, localized magnetic bubbles, some no larger than a city block, that twist and deflect these deadly particles like miniature force fields. These mini-magnetospheres are cosmic riddles, challenging everything we thought we knew about airless worlds and offering a lifeline for future lunar explorers. Scientists first stumbled upon these magnetic quirks during the Apollo missions, when astronauts carrying portable magnetometers noticed erratic readings in certain regions. The most striking example, a patch near the Rheaner Gamma Swirl, a mysterious gleaming feature on the moon's near side. Here, the magnetic field is hundreds of times stronger than the surrounding areas, strong enough to carve a visible bullseye in the lunar dust. Solar wind particles, normally relentless, curve around these zones like water flowing around a rock, leaving the soil beneath oddly pristine. Over eons, this deflection has preserved the swirl's bright surface, shielding it from the darkening effects of constant radiation. What creates these magnetic islands? The leading theory points to the Moon's violent past. Billions of years ago, when molten rock still flowed beneath its crust, asteroid impacts splashed molten material across the surface. As this lava cooled, minerals like iron-rich ilmenite locked in traces of the Moon's ancient global magnetic field, preserving it like a fossil in stone. But the real magic happens when solar wind protons collide with these magnetized rocks. Instead of striking the surface, they're reflected back into space, creating a tiny, shimmering force field, a natural radiation shelter in the most unlikely place. For future lunar bases, these mini magnetospheres could be game changers. Astronauts camping near these zones would face significantly lower radiation doses, reducing cancer risks and equipment malfunctions. Some proposals even suggest artificially amplifying these fields, using superconducting materials to expand their protective reach over habitats, but the implications go deeper. If we can harness this phenomenon, it might reveal how to create magnetic shields for Mars missions or even interstellar travel, turning deadly cosmic rays into manageable background noise. Yet mysteries linger. Why do some magnetic patches produce visible swirls while others, equally strong, leave no mark? Could underground lava tubes, some theorized to be naturally shielded, also harbor similar magnetic properties? And if these fields are remnants of the Moon's primordial magnetism, what other secrets do they hold about our satellite's fiery youth? The Moon's mini magnetospheres are more than curiosities. They're proof that even in the void, nature finds ways to fight back. As solar wind screams across the barren landscape, these silent guardians stand firm, their invisible arms pushing back the storm. For explorers of tomorrow, they might just be the difference between survival and surrender in the cosmos's endless night. NGC 1277 lurks 220 million light-years away in the constellation Perseus, a cosmic relic so ancient it defies everything we know about how galaxies age. This lenticular galaxy, spinning silently in the void, is packed with stars nearly as old as the universe itself, their light tinged red from eons of stellar retirement. Normally, galaxies this massive should be bustling with newborn stars, their spiral arms glittering with blue clusters forged from fresh gas. But NGC 1277 is frozen in time, a celestial museum piece where star formation ceased barely a billion years after the Big Bang. How does a galaxy this big stop evolving while the universe moved on without it? The answer might rewrite cosmic history. Most massive galaxies are cannibals, growing by swallowing smaller neighbors and recycling their gas into new stars. The Milky Way, for example, has absorbed dozens of dwarf galaxies over its lifetime, each collision sparking fresh rounds of stellar birth. But NGC 1277 appears untouched by this cycle, its outer halo suspiciously devoid of the faint stellar streams that betray past mergers. Instead, it's a monolithic fossil, its stars all born in one frenzied burst 12 billion years ago before abruptly shutting down. The smoking gun, its supermassive black hole. Weighing 17 billion suns, one of the heaviest ever measured, it's grotesquely oversized for its galaxy, suggesting NGC 1277 was once the core of a far larger system that somehow got stripped bare, leaving behind only its sterile heart. Then there's the dark matter dilemma. Models predict galaxies this massive should be embedded in vast halos of invisible matter, yet observations suggest NGC 1277 is strangely deficient. Could it have been hurled from a cluster long ago, its dark matter sheared away by gravitational tides? Or is this a rare example of a failed galaxy, one that formed too early, too fast, and burned through its fuel before the universe hit its stride? The implications are staggering. If NGC 1277 isn't alone, if the cosmos hides more of these galactic mummies, our entire timeline of cosmic evolution might be missing a chapter. What's most unsettling is how these relics force us to question galactic life cycles. We've long assumed galaxies evolve steadily, growing and changing over billions of years. But NGC 1277 suggests some might sprint to maturity, then essentially die young, locking their stars in perpetual senescence while the universe froths with activity around them. It's as if we've been reading the cosmos as a linear narrative, only to find entire paragraphs written in a language we don't yet understand. Future telescopes like the James Webb Space Telescope could unveil more of these cosmic anachronisms hiding in plain sight, each one a silent challenge to our celestial storytelling. The universe keeps a ledger of matter, and the books don't add up. For decades, astronomers have faced a cosmic accounting error. Nearly half the ordinary matter predicted by the Big Bang's equations is simply missing. Not dark matter, not exotic particles, but the protons and neutrons that make up everything from stars to smartphones. This isn't some abstract puzzle. It's a gaping hole in our understanding of how the cosmos structures itself. Where could an entire universe's worth of atoms hide? The answer might lie in the most overlooked neighborhoods of existence, the faint, searing webs of gas strung between galaxies. Enter the warm, hot intergalactic medium, or WIM, a ghostly network of million-degree plasma weaving through the cosmic voids like steam from a forgotten kettle. Theorized for years but fiendishly hard to detect, this stuff isn't the thin, cold gas of old models. It's a roiling soup of ionized oxygen, nitrogen, and carbon, atoms stripped bare by collisions and bathed in the afterglow of ancient supernova. The WIM doesn't clump into pretty nebulae or glow like a star. It lingers in spectral whispers, absorbing and re-emitting X-rays at wavelengths so subtle they blur into the background noise of the universe. Catching this phantom matter in action requires cosmic detective work. Astronomers use quasars as backlights, distant beacons whose light pierces the WIM filaments on its way to Earth. As the light travels, specific wavelengths get nibbled away by interactions with the WIM ions, leaving absorption lines in the quasar's spectrum like teeth marks in a cosmic sandwich. The Chandra and XMM Newton telescopes have spotted these fingerprints, particularly from highly ionized oxygen, confirming that the WIM isn't just theoretical filler. It's a real, sprawling reservoir of the universe's missing atoms. But the WIM isn't alone in the cosmic ledger. Some of the missing matter might be lurking in even stranger forms, vast halos of warm gas around individual galaxies, too diffused to glow but too hot to condense into stars. Others could be tied up in faint, fast-moving clouds zipping through intergalactic space, their low density making them nearly invisible to all but the most sensitive radio telescopes. There's even evidence that galactic winds, those violent outflows driven by supernova and black holes, are flinging matter so far into the void it's effectively gone rogue, escaping traditional detection. What makes this hunt so exhilarating isn't just the challenge, it's the implications. If the WIM and its cousins really hold the missing baryons, they could explain how galaxies refuel over cosmic time, siphoning gas from these tenuous filaments like roots tapping underground streams. They might also reveal why some galaxies stop forming stars prematurely, their gas supplies truncated by the ebb and flow of this unseen ocean. Most crucially, they force us to confront how little we truly see. The universe isn't just stars and planets, it's a labyrinth of invisible structure where the majority of ordinary matter exists in forms so elusive we're only now learning to trace its shadow. The next generation of telescopes, like the European Space Agency's Athena mission, promises to sharpen our view, mapping the WIM filaments in unprecedented detail. Until then, the missing matter remains both a frustration and a gift, a reminder that even in an age of stunning cosmic revelation, the universe still keeps its deepest ledgers just out of sight, waiting for us to decipher the fine print. From black holes singing cosmic bass lines to stars that refuse to die, from diamond planets to galaxies made almost entirely of darkness, we've journeyed through 30 of the universe's most bewildering oddities, each one defying expectations and rewriting the rules of reality. These aren't just curiosities, they're cosmic breadcrumbs leading us deeper into the mysteries that make our universe so gloriously unpredictable. Think about it, a hexagon storm raging on Saturn, a zombie star exploding over and over, or an entire galaxy racing toward an invisible force we can't even see. These phenomena don't just challenge science, they remind us how much we still have to learn. What ties them all together, the universe's relentless creativity. It doesn't just follow a script, it improvises, crafting bizarre, beautiful exceptions to every rule we think we've nailed down, and that's the real magic. Every time we point a telescope at the sky, we're not just observing, we're uncovering layers of a story far stranger than fiction. Whether it's the eerie precision of the Einstein cross or the terrifying power of quasar tsunamis, these oddities aren't outliers, they're invitations. Invitations to question, to explore, and to marvel at the fact that reality, even after centuries of study, still has the power to leave us breathless. So here's your challenge, pick the oddity that shook you the most. Was it the Great Attractor dragging galaxies toward the unknown? The Red Rectangle Nebula with its impossible geometry, or maybe the Fermi bubbles towering over our galaxy like silent monuments to some ancient cataclysm? Drop your favorite in the comments. I want to hear which cosmic wonder left you staring at the screen in disbelief. And if this journey through the universe's weirdest corners left you hungry for more, you know what to do. Hit subscribe because the cosmos has plenty more surprises up its sleeve, and we're just getting started. Remember, the universe isn't a museum, it's a live show, constantly evolving, endlessly surprising. So keep looking up, keep wondering, and most of all, keep embracing the beautiful, baffling truth. No matter how much we discover, the cosmos will always have one more secret waiting just beyond the